10.3 Lesson 3 Parametric Equations and Calculus. Our objective for today is you'll be able to find the area of a surface of revolution in parametric form. And of course, we've already seen what a surface of revolution in section 7.4. Theorem 10.9 is what we're learning today. Area of a surface of revolution when you have a curve in the xy plane described by a set of parametric equations revolved about either the x-axis or the y-axis. Although our curve is described by a set of parametric equations, the problem is the same as what we dealt with in section 7.4. The only difference is that in that section, our curve was described by a rectangular equation. So in that section, we took our curve described by a rectangular equation and revolved it about a particular axis of revolution, for example, the x-axis, and we obtain a surface of revolution, and we wanted to find the area of that surface of revolution in section 7.4. We're doing the same thing today. The only difference is our curve is described by a set of parametric equations. So we have the curve starting here at point A, whose x-coordinate is the parametric equation for x evaluated at A, and whose y-coordinate is the parametric equation for y evaluated at A, and ending at point B, whose x-coordinate is the parametric equation for x evaluated at B, and the y-coordinate is the parametric equation for y evaluated at B. So when the parameter t goes from A to B, this arc is traced for our consideration today. And then we're going to revolve that arc about an axis of revolution, for example, the x-axis. And that will give us a surface of revolution, just like we had in section 7.4, and just like we did there, we want to find the area of this surface of revolution. So let's take a look at theorem 10.9, area of a surface of revolution. If a smooth curve C, given by x is equal to f of t and y is equal to g of t, does not cross itself on an interval from t is equal to a to t is equal to b, then the area S of the surface of revolution formed by revolving C about the coordinate axes, meaning the x-axis or the y-axis, is given by the following. And what I'd like for you to do is understand how these definite integrals relate to what we saw in section 7.4. And they're related because we're doing the same problem, surface of revolution, finding the area of a surface of revolution. So you can see that in section 7.4 we had 2 pi, and here we also have 2 pi as a constant outside of the definite integral. The limits of integration are such so that the curve that is being revolved will be traced from a desired point A to a desired point B. So the limits of integration are for that purpose, same as what we considered in section 7.4. And just like we had in section 7.4, we had r of x, and what was r of x? It was the distance between the graph of f and the axis of revolution. So we have the same thing here in section 10.3. We have g of t, which is of course the parametric equation for y, if the axis of revolution is the x-axis. Because if you have the x-axis as the axis of revolution, g of t, where g of t is greater than or equal to 0, would give you the distance from the x-axis to a point on the curve. because g of t would give you the y coordinate of that point. It would be, instead of a here, I should have t. So I have f of t, comma, g of t, and that would give me, g of t would give me the y coordinate of a point on the curve. And of course, the y coordinate tells me the distance from the x-axis to that point. And that's what I have here, g of t, corresponding to r of x from the integration formula from section 7.4 for area of a surface of revolution. R of x was the distance between the graph of f and the axis of revolution. So if the axis of revolution now is the x-axis, g of t tells us the distance from the axis of revolution to a point on the curve. Going back to what we saw in section 7.4, this particular part of the integrand came from the definition of arc length. And the reason for that is because when we came up with the definition of arc length, we used line segments to approximate the length of the arc, and then we went through our derivation process to come up with this definition of arc length. And when we began to approximate the area of a surface of revolution, we also began with a line segment, which was rotated to give us a frustum of a right circular cone, and the length of that line segment was a part of the pre-calculus formula for finding the lateral surface area of a frustum of a right circular cone, and as a result of that, it carried over into our integration formula because it came from the length of a line segment, just like this particular integrand for definition of arc length also ultimately can be traced to the length of a line segment. And because we're dealing with the same problem, we have the same situation when we're considering an arc that is given by a set of parametric equations in section 10.3. Just like we had this particular part of the integrand in 7.4 relating to the integrand from the definition of arc length, if you look over here, this part of the integrand in theorem 10.9 is coming from the integrand for arc length in parametric form from theorem 10.8. So let's read again, theorem 10.9, area of a surface of revolution. If a smooth curve C, given by a set of parametric equations, does not cross itself on an interval from t is equal to a to t is equal to b, then the area S of the surface of revolution formed by revolving the curve about the coordinate axes is given by the following. Revolution about the x-axis, where g of t is greater than or equal to 0, and this particular part of the integration formula is giving us the distance from the axis of revolution to a point on the curve, and which I have shown here in green, and now I'm tracing it in gold. It is this distance from the axis of revolution, the x-axis, to a point on the curve. And we have 2 pi, just like we had in section 7.4, and we have this factor of the integrand coming from the integrand for arc length in parametric form, and we had the same parallel in section 7.4. The limits of integration are from a to b, tracing the arc that will be revolved about your axis of revolution. What if we change the axis of revolution to the y-axis? And we will consider f of t greater than or equal to 0. In other words, we're looking at an arc that's on the right side of the y-axis. And just like we had in section 7.4, where r of x gave the distance between the graph and the axis of revolution, in number 2 here, we have f of t what is f of t? It is the x-coordinate of a point on the arc. And f of t will give us the distance from the axis of revolution, which in the second case is the y-axis, to a point on the curve. So that's where the f of t comes from. Just like we had r of x in 7.4, it's giving us the distance from the y-axis to a point on the curve. And of course, we have 2 pi, and we've already talked about the parallels between what we're seeing in 10.3 and what we saw in 7.4. And we also have this particular factor of the integrand, which we saw as the integrand for arc length in parametric form, and we observed the parallel situation in 7.4. The limits of integration will trace the curve that will be revolved to give us our surface of revolution. We will take a look at example 6, and we will take a look at a modified version of example 6 where we change the axis of revolution to the y-axis. But let's look at the example 6 as it is in the textbook. Finding the area of a surface of revolution. So the instructions for the problem state, let C be the arc of the circle x squared plus y squared is equal to 9 from 3, 0 to 3 halves, comma, 3 square root of 3 over 2 as shown in the figure. So here is 3, 0, and here is 3 halves, 3 square root of 3 over 2, and we take this arc and we're going to revolve this arc about the x-axis to obtain our surface of revolution that is shown in the diagram. Find the area of the surface formed by revolving the curve about the x-axis. So it says here you can represent the curve parametrically by the equations. So this would be given in a problem. So even though the example is giving you a rectangular equation, the problems that you'll be doing tonight, you will be given the set of parametric equations to begin with. So we will start here. So let's say you're given that this is your set of parametric equations, and the interval for the parameter is from 0 to pi over 3, and on that interval for the parameter, this arc will be traced. And then you want to take that arc and revolve it about the x-axis to obtain this surface of revolution, and we want to find the area of this surface of revolution. So that would be given to begin the problem. Our next step is to apply theorem 10.9 and write a definite integral that would give us the area of our surface of revolution. So in the definite integral, we have our constant factor of 2 pi. The limits of integration, as it is given in the problem, when t goes from 0 to pi over 3, this arc that we're going to revolve is traced, which I showed in green just now. So the limits of integration will be from 0 to pi over 3. And the next part of the integrand that we want to consider is g of t, which would tell us the distance from the axis of revolution, the x-axis, to a point on our curve. And that distance is given by the y-coordinate of the point, which is, of course, g of t, or 3 times sine of t. So that's how we have 3 times sine of t here. And this particular part of the integrand that we want to look at next, how do we find that? You have to find the derivative of the parametric equation for x with respect to t and square it. You have to find the derivative of the parametric equation for y with respect to t and square it. That would go for dx dt squared and dy dt squared. You have to add those two and then take the square root. So we have x is equal to 3 times cosine t. So dx dt will be equal to negative 3 sine t And when you square dx dt, you will get 9 sine squared t. The square of negative 3 is 9, and the square of sine is sine squared t. And now you need to figure out what dy dt squared is. We begin with the parametric equation for y. Y is equal to 3 times sine t. Dy dt would be 3 times the derivative of sine is cosine. And then we have to square that. So we have dy dt squared is going to be 9 times cosine squared t. So now we're going to go ahead and substitute dx dt squared and dy dt squared into the integration formula for finding the area of a surface of revolution. So we have 2 pi, and then we have g of t, which is 3 times sine of t. The limits of integration are from 0 to pi over 3. And then we have the square root of dx dt. So that's how we have the square of dx dt, which we've already found to be 9 sine squared t, plus the square of dy dt. Here's dy dt, and of course we've already found the square of dy dt to be 9 cosine squared t. So that simplifies to, in the radicand, you can factor out the common factor of 9 from these two terms. And when you do that, you get 9 times sine squared t plus cosine squared t. And then you have the square root of a product, so you can write that as the square root of 9 times the square root of sine squared t plus cosine squared t. The square root of 9 is 3. And you will remember a Pythagorean identity from trigonometry. Sine squared t plus cosine squared t is equal to 1. So we actually have the square root of 1, which is, of course, 1. So this quantity here simplifies to 3 times 1, which is, of course, 3. And then you have 3 sine t times 3 is 9. And then you have 9 times 2 is 18. Three times 3 is 6. 6 times 2 is 18. So we have 18 pi times the definite integral from 0 to pi over 3 of sine t dt. And now we need to find an antiderivative of sine. The function whose derivative is sine is negative cosine. The derivative of cosine is negative sine, so the derivative of negative cosine is positive sine. So we have 18 pi. Applying the fundamental theorem of calculus, the antiderivative is negative cosine. And we're going to evaluate that at pi over 3 and 0 and subtract. So we have s is equal to 18 pi times cosine of pi over 3 is 1/2. So you have negative 1/2 minus cosine of 0 is 1. So you have minus negative 1. So you have 18 pi times negative 1/2 minus negative 1 is negative 1/2 plus 1, which is positive 1/2. So the surface area is half of 18 pi, or 9 pi, and you can write square units if you would like to. Square units, because we are finding surface area. Now let's look at a modified version of example 6 where we change the axis of revolution to the y-axis. So we begin with our definite integral for finding the area of a surface of revolution. We know our limits of integration because it is stated in the problem that t is going from 0 to pi over 3. And because the axis of revolution is the y-axis, which is over here, and this is now our axis of revolution, and here's our curve, which I am tracing in gold, and we want to revolve it about the y-axis. So this particular part of the integrand is due to f of t being the x-coordinate, and the x-coordinate of the point will tell us how far this point is from the axis of revolution, which in this problem is the y-axis. So that's why we have f of t there. So we're going to write f of t is the parametric equation for x. It's 3 cosine of t. And then we have the square root of dx dt squared, which we saw in the previous part, is 9 sine squared t plus dy dt squared, which we saw in the previous part, is 9 cosine squared t, and we have dt. So we write s is equal to 2 pi times the definite integral from 0 to pi over 3, 3 cosine t, and as we saw in the previous example, this particular quantity will simplify to 3. So we have times 3 dt, and then you can multiply the constant factors together. 3 times 3 is 9, and 9 times 2 is 18. That gives us the surface area is 18 pi times the definite integral from 0 to pi over 3 of cosine t dt. What's an antiderivative of cosine? Sine, because the derivative of sine is cosine. So now we use some basic trigonometry. Sine of pi over 3 is square root of 3 over 2 minus sine of 0, which is 0. So when we multiply, 18 divided by 2 is 9, so we have 9 square root of 3 pi square units. Nine square root of 3 pi square units. When you compare this answer to the answer that we had for the unmodified version of example 6, where the axis of revolution was the x-axis, the answer for that was 9 pi square units. So this is actually a larger surface area because we have 9 pi times square root of 3, and square root of 3 is greater than 1. So we've done the objective. You'll be able to find the area of a surface of revolution in parametric form. We will conclude our lesson by looking at number 21, which is not related to the objective. Find the equations of the tangent lines at the point where the curve crosses itself. But we're looking at it because you will have problems like this on the homework for tonight. Find the equations of the tangent lines at the point where the curve crosses itself. So where does the curve cross itself? You should begin this problem by graphing this set of parametric equations by using your graphing calculator or Desmos. Find the equations of the tangent lines at the point where the curve crosses itself. So we're going to graph our parametric equations using Desmos to find where the curve will cross itself. So you can see that I've entered my set of parametric equations as an ordered pair into Desmos, and we're going to look at the graph, the curve for this set of parametric equations when the parameter goes from 0 to pi, and the curve that we get is what you see here in red, and it is traced as you see here. So where does the curve cross itself? It appears that the curve is crossing itself at the origin at 0, 0. And yes, it does happen. And you know that from the graph. But what happens if you consider the graph of the parametric equations on the interval from, what happens when you consider the curve given by the set of parametric equations when the parameter t goes from 0 to pi over, or from 0 to 2 pi? So when the parameter went from 0 to pi, we had the loop that was traced earlier, and it is shown here in red. And when the parameter goes from 0 to 2 pi, well, it goes from 0 to pi first, as you saw traced in my first graph that I shared with you earlier, and the point of intersection where the curve crosses itself is at the origin. And then when the parameter goes from pi to 2 pi, you have this part of the curve traced here in blue. And it comes back to the origin. So if you go from 0 to 2 pi, you get that figure that looks like an 8. But it crosses the origin twice. And then if you look at graphing the set of parametric equations on the interval from 2 pi to 3 pi, you will get this loop again. So when you go from 0 to 3 pi, this is how the curve is being traced. You start here at the parameter t equal to 0. You get to the origin again when the parameter is pi. And then you keep tracing, and you get to the origin once again when the parameter is 2 pi. And then you keep tracing. You repeat the loop that you had from the first interval, and you get to the origin again when the parameter is 3 pi. And if you do it one more time to go from the interval from t is equal to 3 pi to 4 pi, what you will see is, once again, that, and I'll do this in black ink, that the bottom half of the loop is traced again, and you get back to the origin at t is equal to 4 pi. So what is it that we want to do in this problem? We want to find the equations of the tangent lines at the point where the curve crosses itself. So the curve crosses itself at the origin, but there are actually going to be two tangent lines that we have to consider. And why is that? And here's the reason. As we go from 0 to pi, the curve crosses itself at the origin, and you can see from the orientation of the curve that the tangent line at the origin corresponding to t is equal to pi will be the green line that I just sketched now. And that happens when the parameter t is equal to pi and we are at the origin. If you keep going, then you will once again end up at the origin, but that happens when the parameter is now 2 pi, but however, because of the orientation of the curve as you are approaching the origin, the tangent line will now be the gold line that I am showing you. And of course, they have different slopes. So you have to find the slope of each tangent line first. Find slope. And then we know that the point that the tangent line passes through is, of course, the origin, 0, 0, and you can substitute that into the slope, the point slope form of the equation of a line. The point slope form of the equation of a line. So you will substitute 0 for x sub 1 and 0 for y sub 1, and whatever the slope of the tangent line is. Now, if you're not sure about what the orientation of the curve is, you can use Desmos to change the parameter from t to a and then add a slider, and you can use the slider to see how the curve is traced. So to find the slope of each tangent line, we need to use theorem 10.7, parametric form of the derivative. We need to find dy dx and then evaluate it at t is equal to pi to find the slope of the green tangent line. Substitute that for m in our point slope form, and substitute the coordinates of the origin, 0, 0, to get our equation of the tangent line at the point where the curve crosses itself. And then we have to repeat the process where we evaluate the derivative at t is equal to 2 pi, find the slope of the gold tangent line, substitute for m here, and
Mr. Wu, your screen is not showing.
So find the slope of the tangent line, the gold tangent line, by evaluating dy dx at t is equal to 2 pi, substitute for m here in point slope form, and the coordinates of the origin for x sub 1 and y sub 1. So we will now do part 1, and we will begin with the parametric form of the derivative. So we have the parametric form of the derivative. We need to find dy dt. So to find dy dt, you're going to have the derivative of sine is cosine. So that's dy dt 3 times cosine t. And dx dt, you're going to have to use the chain rule, because what you have here is a composition of functions where the inside function is 2t, and of course you do have a constant multiple of a 2 as well. So you have 2 times the derivative of the outside function sine is cosine, so you have cosine of 2t, and then you have to use the chain rule and multiply by the derivative with respect to t of the inside function 2t, which is of course 2. And then you have 2 times 2 is 4. So now we have dy dx, and we can use that to help us find the slope that we need for each of our 2 tangent lines. So now we have to evaluate dy dx at t equal to pi to find the slope of the green tangent line. So now we have 3 times cosine of pi over 4 times cosine of 2 pi. Cosine of pi is -1, so in the numerator we have -3. In the denominator we have cosine of 2 pi, which is +1, so in the denominator we have 4 times 1, and the slope of the green tangent line is negative 3/4, and you would expect the slope to be negative because you can see that the green tangent line is sloping downwards. So when we write our, what is it that we want? Look at the instructions. Find the equations of the tangent lines at the point where the curve crosses itself. So we have two tangent lines, and for the green tangent line, the equation will be y minus y sub 1 is equal to negative 3/4 times x minus x sub 1, or we just have y is equal to negative 3/4 x. That's the equation of the green tangent line. So now to find the equation of the gold tangent line, we have to evaluate our derivative dy dx at t is equal to 2 pi. And of course, the reason we have to do that is because at t is equal to 2 pi, we get to the origin once again, but we're approaching it from a different direction. So the tangent line to the curve at t is equal to 2 pi will have a different slope than what we just saw. So we have dy dt evaluated at 2 pi, so we have 3 times cosine of 2 pi divided by dx dt evaluated at 2 pi, 4 times cosine of 2 times 2 pi is 4 pi. So cosine of 2 pi is 1, so 3 times 1 is 3. Cosine of 4 pi is also 1, 4 times 1 is 4. So the slope of the gold tangent line is positive 3/4. So now if you want to write an equation for the gold tangent line, you can use the point slope form, and you can write y minus 0 is equal to m 3/4 times x minus 0, or just y is equal to 3/4 x. So we were able to write equations of the tangent lines at the point where the curve crosses itself. We began by graphing the curve using Desmos. We observed where the curve was crossing itself, and we also had to determine the value of the parameter at which the curve was crossing itself, because that was needed to find the slope of the tangent line in each of our two cases. The first tangent line is the green one at t is equal to pi, and the second tangent line is the gold one at t is equal to 2 pi. And then once we used the parametric form of the derivative to find dy dx, we evaluated dy dx at the corresponding value of the parameter to find the slope of each tangent line, and then we took that slope and used the point slope form of the equation of a line along with the coordinates of the point to find our equations.